Hey folks, welcome back. Today we are going to talk about Module 2, Part 2. We're going to discuss logic gates. Okay, so a logic gate is used to actually make decisions in a computer. So all CPUs are made up of, as we've discussed, an ALU. The ALU is the arithmetic and logic unit, and that part of the computer is capable of adding numbers together. So the question is, how does that actually work? How can you add numbers just using electricity? And the answer to that is using gates. So gates are allowing particular power to come in one of multiple places and to give you an answer back depending on what it is that you did. So we're going to talk about three basic gates, and then by the end of this I'm going to show you how you can add them together using a cool little simulator to show you how you can build a machine that can add two numbers. So the first thing to understand is that all of these gates are going to work on Boolean values. So the term Boolean comes from George Boole, and he was one of the people who came across this idea, who is speaking of whether or not we have power or no power, or true or false, or 0 or 1. They all mean the same thing. So the idea is, but Boolean values can only be in one of two states. Either there is power, and it's a 1, or it's true, or there's no power and it's a 0 or it's false. So false, 0, and no power all mean the same thing. True, 1, and yes, there is power all mean the same thing as far as this conversation is concerned. So a Boolean gate works on true and false. So the first Boolean gate that we're going to look at is called an AND gate. An AND gate decides whether there is power coming in on both lines at the same moment. When each of these is going to have a symbol, and I want you to get familiar with the symbol because you will eventually need it as time goes on. So the symbol for an AND gate is what's drawn over here. The way that to remember this is that the word AND ends in a D. And to me, this has always looked like a capital D. It's a capital D that happens to have a line out the front and two lines in the back. Those are the wires that are coming in, and this is the wire that's going out. And so the way that the AND gate works is, if there is power coming in on both of these lines, the AND gate will allow power to go out on the front. If there's only power on one line, nothing comes out the front. And if there's power on no line, nothing comes out the front. So the only way that this sends power out is if power was coming in from both of these two separate inputs. So an AND gate has two inputs and one output. And basically what it does is, if there's power on both of them, it will send power out. I'm going to show you this cool little website, which we're going to use during today's lecture. The URL is right there at the top of the screen. And so you can see that if you want to type it into your browser and play with it as well. There's also a link for it later on in the slide deck. So the thing that's neat about this site is it allows you to add the different gates onto the screen and see what happens. So we have an input, which is a switch that can either be turned on or off, and we have an output, and we can connect wires in between. So what I'm going to do is, up on the right-hand side here, I'm going to ask it to give me an AND gate. I'm going to say add that node. And so you can see it drew exactly what I drew on the screen previously. This is the universal symbol for an AND gate. It has two wires that come into it. So I'm going to connect this wire by just dragging it down to here. And I need another input switch because I'm going to eventually need to be able to have two different inputs. So I'm going to add another input switch to my diagram. And I'm going to drag it down here. And I'm going to connect that input switch to the second wire. And then finally, I'm going to output from the output side of it into my little output diagram. So all I did was I connected some wires together on my gate. So now what I'm going to do is I'm going to turn on one of my two switches, and notice that the output did not light up. I'm going to turn it off, I'm going to turn on the other one, and notice that the output still did not light up. But now I'm going to turn both of them on together, and all of a sudden the output lights up. And if I turn off either one of them, it goes off. So this really demonstrates the usefulness of an AND gate. It shows me that unless power is coming in on both of my inputs, I don't get any output. And if both of them are 0 or both of them are false, my output is also false. So that's pretty cool. So an AND gate is a device that, if power is coming in on both sides, you will get power on the outside. And the reason it's called an AND gate is because if you think about it in English, it works the same way. If I say, in order to pass this class, you must pass all the projects and all the tests, you understand that if you pass all the projects but don't pass all the tests, you don't pass the class. If you pass all the tests but don't pass all the projects, you don't pass the class. You only pass the class if both of the things are true. You only send power out if both of the inputs are true. It works exactly the same way. I will say in English we're a bit sloppy about some of these things, and sometimes we don't literally mean and, so this analogy works for this exact example, but there are examples you can think of where the and works slightly differently. All right, so an AND gate works by checking to see if both of the inputs are true or 1, or both of the inputs are sending power. And if so, it sends power out to the back end. So how is an AND gate useful in the real world? Well, we're going to see as you add these together, you can do cool things with them. Very specifically, it's actually quite easy to make a mechanical device that works like this. If you think about it, it's effectively just taking a certain amount of power in, and when both of them are on, you're getting double the power into the inputs, and it sends the power out. So it's acting like a gate, which is where the name comes from. If you have enough power, it comes out the other side, but only if you have enough. If you only have one or the other, it doesn't come out. So it's actually quite easy to make this in hardware, and once you've made this, you're going to see as we go further on that you can do all kinds of cool things with it. All right, so this is just explaining this slide, what I just did in the simulator. That's the URL to the site that allows you to do this. I would recommend you click on that URL, and I would recommend that you then build yourself the same system and make sure that you see that it works the way that I just described. And then this is just an animation that shows you pretty much what I just did a moment ago, where turning on either one of them does nothing, but if you turn on both of them, then the power comes through. All right. We can write a truth table for an AND gate. And all that we're doing here is we're just enumerating what all of the possible outputs are. And so what we're saying here is we have two inputs. This is input number 1, and this is input number 2. And then we've one output. If the input number 1 is a 0, and input number 2 is a 0, we output a 0. If input 1 is a 0 and input 2 is a 1, we still output a 0. If input 1 is a 1 and input 2 is a 0, well, we still output a 0. So the only time that we output a 1 is if both input 1 and input 2 are 1. This truth table, again, seems very obvious when you're looking at it, but it's probably what you need to remember in order to be able to answer questions on the tests. AND gates will only return a 1 if both input 1 and input 2 are a 1. In all of the circumstances, no matter what you do, it returns a 0. That's the short version of what an AND gate does. Okay, so that's AND gates. What else you got? So the next one we're going to talk about is an OR gate. An OR gate passes values through if either or of the inputs is true. So again, it has a drawing. This one I don't have a clever thing for you because it's just kind of like a squished AND gate. It kind of looks like somebody drew an AND gate and then they sat on the AND gate and squished it down, and you ended up with this weird squishy bit and the inside started to cave in. I guess it's a heavy person, not what the image drawn was, but anyway, there you go. My art skills are not high. So an OR gate is created by having two inputs, one output, and it's drawn with this weird kind of concave V-looking thing that has two inputs on one side and one input on the other side. So what is the functionality of an OR gate? Well, as we said, if either side is true, the output is true. So you can see here, if I turn on either one of them, the output becomes true. And even with both of them turned on, the output is still true. So one of them is sufficient to make it true, and either one will work. Doesn't matter which one you give me. All right, so the truth table for an OR gate is you're going to get a 1 in every case except if you give it two zeros. Everything else yields a 1. You only get a 0 if you're given two zeros. And that's the short version of the OR gate. All right, so that gave us AND gates, and that gave us OR gates. What else you got? Well, we got one more basic gate, which is called a NOT gate. and it's drawn like a person's on their side. And so it's a triangle with a circle and a line on front of it. The OR gate and the AND gate both had two inputs, but the first thing to notice about a NOT gate is that it only has one input. One input, one output. And what it does is it reverses whatever you send in. So if you send in a 1 or a true, it returns a 0. If you send in a 0, it returns a 1. So it basically reverses whatever you give it. And that might seem not particularly useful, but I promise you it is. So here's the NOT gate in action, and you can see it's basically just flip-flopping whatever input I give it. All right, so truth table for that one's very simple. Input 0, output 1. Input 1, output 0. There's really no way that I can simplify that beyond that. So that gave me 3 gates. We've talked about AND, OR, and NOT. Believe it or not, if you have those 3 gates, you can build the computer that you are currently sitting on front of. Because the computer you're currently sitting on front of is just a very, very, very large, complicated combination of those gates. But the 3 of those are the basic fundamental building blocks of a computer. And so we're going to talk about how we can put this together. The important part of this lecture is that you understand the 3 gates and you understand the inputs and outputs. What I'm about to show you is how you can use those gates to do interesting things. You're not going to be expected to produce anything that's in the last part of this slide, but I want you to understand how it works because otherwise this just seems like an abstract thing that doesn't have any purpose. So let's imagine I want to add 2 numbers. I want to add the number 1 and 2 in decimal. Well, we all know that 1 plus 2 is equal to 3. That's no news to anybody. If I convert each of these into binary, 1 will be 0, 1, 2 will be 1, 0, and just like in everything else in the world, it works the same way when you're adding them. 0, 1 plus 1, 0, you just add the 2 decimals. 0 plus 1 is 1, 1 plus 0 is 1, and so your answer is 1, 1, and if you convert that back, we know that gives you a 3. So you can add numbers in binary just like you can add them in decimal. It works really decently. So let's do a bigger number to convert here, just so that we can see an example. So we start off with 01101, and we're going to add to it 01010. All right, so we start off with the first 2 digits, the 1 and the 0. The one's on the right-hand side. When you add them together, you get a 1. That's easy enough. When you add the next 2 digits, which is, again, a 0 and a 1, it's going to work the same way. 1 plus 0 is 1. When you add the next 2 digits, same thing is going to happen. 1 plus 0 is 1. So far, nothing exciting has happened, but we're about to see how it works when we do the next 2 digits. So this time we have a 1 and a 1. And the problem is we can't represent that as a 2 because we don't have 2's. So what we have to do is we have to represent it as a 0 and carry 1 onto the next addition. So we put the 0 down, and then we're going to carry 1 over to the next place. And this is the same as what happens when you're adding a 9 and a 1 in decimal, right? If you have a 9 and a 1, you can't represent that with a single digit, so you represent it as 1, 0. All right, so based on that, we're going to add 1 plus 1 gave me a 0, and then when I carry the 1 over, I get 1 again. So we're left with 01101 plus 01010, 01101, which is the first number, plus 01010 is equal to 10111. And if we go and we convert all of those numbers back into decimal, let's check and see if that worked. So if we take the individual parts of this number and we convert that back, this is a 1, that would have been a 2, that's a 4, that's an 8. So effectively we're adding 8 plus 4 plus 1, and when we add those together we get 13. In this case, that's a 2, and that's a 8. So we add 2 and 8 together, and that gives us 10. So effectively, the original question was 13 plus 10. And when we convert this back together, this is 1, 2, 4, 8, 16. So it's going to be 16 plus 4 plus 2 plus 1, which is 23. And of course, 10 plus 13 is 23. So my point here is that you can do math with binary just like you can do math with decimal. And hopefully that made sense to you. You can certainly make up other numbers and you can test them yourself to make sure you understood it. But it's working exactly the same way. You just have to remember to add new digits over to the left anytime that you exceed the digits that you have. So what does all this have to do with logic gates? And why are we talking about this? Well, how can we make a machine that does this with logic gates? Well, let's take a look at the original digits. So assuming we're just dealing with one digit that we want to add to one other digit, there are four possibilities. We have 0, 0, which gave us a 0. We had a 0 and a 1, which gave us a 1. We have a 1 and a 0, which gave us a 1. And then we had this weird one, which was a 1 and a 1, which gave us a 0 with a carry of 1. And if we look at this truth table, or if we look at this as a truth table, this is almost exactly an OR gate. The OR gate was 0, 0 gave you 0. 0, 1 gave you 1, 1, 0 gave you 1, and 1, 1 gave you 1. This is correct, this is correct, this is correct. These all match over here, but this one gave us the wrong answer. 1, 1 does not give you 1, it's supposed to give you 0. So it's almost right, but it's not quite right. So what we need here is something called an exclusive OR. We only want to get a 1 out when exactly one of them, when exactly one input was a 1. Otherwise, we want to get a 0. And that's called an exclusive OR. Well, it turns out you can build an exclusive OR just using the previous things that we've already known about. So this is the circuit diagram for an exclusive OR. You're not going to be required to reproduce this circuit. So don't get scared looking at this. But all that's going on in here is I have a couple of OR gates, a couple of AND gates, and a couple of NOTs. And if you put them together in this particular way, you can see that we can produce a device which, if you look at the animation, if either one of the inputs is on, then the output is on. But if I turn both of the inputs on, the output turns back off again. And so this is called an exclusive OR. It actually has its own symbol as well, which is not particularly important, but this is the symbol for an exclusive OR. It happens commonly enough that instead of having to draw that whole diagram every time, they just gave it its own unique symbol. And so all of what you're seeing here on this screen is now represented by this weird little symbol, which has that 2 lines at the front. So now that we have exclusive ORs, you suddenly can see how you can add 2 digits together, because the exclusive OR gives me everything that I wanted plus the carry. And so this little design here on the screen, where I'm using an exclusive OR, so this part of it can be replaced by the diagram you saw on the previous chart, or you can just use the exclusive OR gate because the program supports it. If you simply have an AND gate, this is an AND, and this is an exclusive OR, or it's abbreviated XOR. If you use those two in this particular circuit, you actually get a adder. This circuit will add 2 one-digit numbers together for you. So if you give it 1 and a 0, this will output 1. If you give it a 0 and a 1, it will output 1. If you give it a 0 and a 0, it outputs 0. And finally, if you give it a 1 and a 1, it outputs 0, but it does represent that there's a carry. So you'll see here in a moment, I'll light up both of the inputs. And now you notice that the output is off, but the carry was turned on. This adds 2 digits together. And all you're using is AND gates, OR gates, NOT gates in a very particular combination. If you want to add 2 two-digit numbers, you just take 2 of these and you combine them. The carry becomes an input into the next one, and then you have 2 more inputs. And so you can push these together to add a 2-bit number. A bit is a 1 or a 0. So a 1-bit number is this, what we're dealing with here, 0 plus 1, 1 plus 0, and so on. A 2-bit number would be 0, 0 plus 1, 0. That would be 2 2-bit numbers. A 3-bit number would be 101 plus 100 or something along those lines. And so you can just keep combining these over and over again to make a 1-bit adder, which is what this is, a 2-bit adder, a 3-bit adder, or you can go all the way up to a 16-bit adder. You can even go to a 32-bit adder or even a 64-bit adder. So yes, there's going to be a lot of gates by the time that you get to 64, but it means you can add two very large numbers instantaneously just by seeing where electricity flows. And all you're doing is combining different ands, ors, and nots. And so that is how the arithmetic and logic unit works inside of your CPU. Each of these gates is implemented using a transistor. And the transistor can specify whether it's an AND gate or an OR gate or whether it is an XOR gate. And you just build lots of them with little tiny wires inside of the circuit in order to be able to build a device that can add numbers. And once you can add numbers, you can subtract because all you have to do is put a negative sign in front of one and then you can do subtract. And you can do multiplication because all you're doing is adding over and over again to do multiplication. And you can do division because there's a way to do that as well. And so on and so on and so forth. So the important thing to get out of this is I wanted you to understand how the internals of the CPU works, but we're not expecting you to be able to produce a CPU or anything like that. Although based on what you've learned today, you actually could if you sat down and did it. But what we do care is that you understand what an AND gate is, what an OR gate is, what a NOT gate is, and you understand the truth tables from each of those. We're not going to test you on the adder circuit or the XOR gate. Those are not going to be in any test or quiz that you're going to have, but we certainly will test you on the AND or NOT and the truth table as well. So that completes today's lecture where you've learned about the different parts of logic gates. They are very useful because they are effectively how computers are built. And it is all based on each of those three things. Our friend the AND gate, which looks like a D because of AND, A and D. Our friend the OR gate, which looks like a D that's been squished. And then our friend the NOT gate, which just looks like an alien or something. I'm not really sure. Those three things combined allow you to build a machine that adds things together. So that completes today's lecture. I will see you